Dear students, welcome to the third lecture of linear algebra. In this lecture, we are going to explore linearly dependent and independent vectors with some properties and basis of a vector space and dimension of a vector space. Firstly, we start with the definition of linearly dependent vectors. If V is a vector space over F and V1, V2 and so on Vn be vectors in a capital V, then we say that they are linearly dependent over a field F if there exist elements lambda 1, lambda 2 and so on lambda n in F, not all of them are 0 such that their linear combination becomes 0. It means if we consider set of vectors, then they are said to be linearly dependent if by using some non-zero scalars it is possible to write their linear combination becomes 0. For example, if we consider the vector space C over R, then if we consider the set which contains the vector v1 is equal to 1, vector v2 is equal to suppose I, and another vector is v3 is equal to something like 2 plus 3i. Okay, in this case it is possible to find the scalars. Suppose for example lambda 1 is equal to 2, then lambda 2 is equal to 3 and lambda 3 is equal to -1. In this case, if we consider the linear combination, for example lambda 1 into v1 plus lambda 2 into v2 plus lambda 3 into v3, then it is equal to lambda 1 means 2 and v1 is 1, so we have this something like 2, then we have 3 and v2 is I, so 2 plus 3i, and then lambda 3 is -1, so it is minus, and v3 is 2 plus 3i, so it becomes 2 minus 3i and it is equal to 0. So in this case it is possible to write the linear combination of these vectors with these non-zero scalars is equal to 0, and thus we say that this set, which is subset of set of all complex number as a vector space over R, becomes linearly dependent. Now we consider the definition of linearly independent vectors. If the set of vectors, that is v1, v2 and so on vn, are not linearly dependent over a field F, then we say that the set is linearly independent. Again, for example, if we consider the space R2 over R, and if we consider the set of vectors, for example v1 is the first vector which is 1 0, and another vector v2 is 0 1, then if we consider their linear combination, for example lambda 1 into v1 plus lambda 2 into v2 is equal to 0, then this implies that lambda 1 into v1, so we write here lambda 1, v1 is 1 0, then we have lambda 2 which is lambda 2 into 0 1, and if we equate to 0, then this implies that we know that how to multiply the scalar to the vector in R2 and how to add the vectors in R2. And then by using the definition of scalar multiplication and addition in R2, we finally write it as lambda 1 comma lambda 2 which is equal to 0, and obviously this implies that lambda 1 is equal to 0 and lambda 2 is equal to 0. So by using some non-zero scalars, it is not possible to write their linear combination becomes 0. So in this case we say that this set is not going to be a linearly dependent, and hence it must be a linearly independent. Now we consider some important results regarding linearly independent and independent vectors. The first one is if the set of vectors v1, v2 and so on vn are in capital V are linearly independent over a field F, then every element in their linear span has unique representation of this form with lambda I belongs to F. It means that if we try to write the vector, same vector in different way, for example lambda 1 dash v1 plus lambda 2 dash v2 and so on lambda n dash vn, then in that case it is quite easy to show that lambda 1 is equal to lambda 1 dash and so on lambda n is equal to lambda n dash by using the property that our vectors are linearly independent. So this is one of the important result. Also, if you consider the second result, which says that if we have set of vectors v1, v2 and so on up to vn are in V, then either they are linearly independent or some vk is a linear combination of preceding ones, that is v1, v2 and so on vk. So this result is again quite simple to prove, because if we have a set of vectors and if it is linearly dependent, then obviously there are if we consider the linear combination, if it is equal to 0, then some scalars must be non-zero. Okay, and try to find out the largest k such that the scalar becomes non-zero, and obviously that vk can be always expressed as a linear combination of preceding ones. We consider this result also. If the set of vectors v1, v2 and so on vn in V have w as a linear span, means if we consider span of these vectors, we'll get the linear span which is suppose w, and if we have vectors v1, v2 and so on vk that are linearly independent, means this set is a subset of the original set having span is a w, then it is always possible to find a subset of this original set v1, v2 and so on vn, which is of the form v1, v2 and so on vk, and we add some vectors like vi1, vi2 and so on vir, consisting of linearly independent elements whose linear span is also w. It means if we have a set of vectors having some span w, and if we have a subset of this set which is linearly independent, then by adding some vectors to that set such that the set becomes again linearly independent and that its span is capital W. So it is always possible to add some vector, because originally this set is a linearly independent and we try to add the another vector, for example vi1, such that this set becomes linearly independent. Okay, and all the way it is always if you add some vector in that and the set is linearly independent, then again try to add some other vector also, and in such a way we'll get the set of vectors such that the set becomes linearly independent and the span is also equal to capital W. Now we consider the second result. In this result, it says that if V is a finite dimensional vector space, then it contains a finite set of vectors v1, v2 and so on vn of linearly independent elements whose linear span is capital W. Now we consider definition of basis of a vector space. We say that a subset S of a vector space V is a basis of V if that set S is linearly independent and that its span is the whole space capital V. For example, if we consider the vector space C over R, okay, and particularly if we choose the vectors v1 is equal to 1 and v2 is equal to I, then we know that this set is linearly independent, and if we consider its a span, suppose we call it as a S, then the span of S is alpha v1 plus beta v2, such that alpha beta are real numbers. It means if we consider the addition as scalar multiplication in a set of all complex numbers, then it becomes alpha plus I beta such that alpha beta belongs to R. and in fact this is equal to set of all complex numbers. It means this set is linearly independent and its span is whole space C. Therefore we say that this set is the basis of the vector space C over R. Now we consider some important results regarding the basis of a vector space. If V is a finite dimensional vector space and u1, u2 and so on un be span of V, then some subset of the set forms a basis, because we know that this set span whole space V, and if it is linearly independent, then this becomes a basis. If it is not linearly independent, then remove some vectors from this set so that this set becomes linearly independent, and in that case it is going to be linearly independent and also spans whole space V, and therefore we'll get some subset of this set such that it forms the basis of the vector space V. Similarly, we have other result, that is, if set v1, v2 and so on vn is a basis of V over a field F, and if w1, w2 and so on wm are in V such that they are linearly independent, then we have this result, that is m is always less than or equal to n. So if basis contains n vectors and if we have any set of vectors which is linearly independent, then number of such a vector is either equal to n or less than that number. So this is another important result with respect to the linearly dependent and independent vectors and basis. Now we consider this third result. If V is a finite dimensional over F, then any two bases of V have same number of elements. It means, for example, we know that for the space C over R, one may write the set of vector 1 and I is the basis of the particular vector space, and maybe something like 2 plus 3i is also going to be a basis of a vector space, but the number of vectors in the basis must be same. And now the fourth one, if V is a finite dimensional over F, then V is isomorphic to Fn. V is isomorphic to Fn for some unique integer n. In fact, this n is the number of element in the basis of V over F. Number of elements in the basis of V over F. Now we consider the definition of dimension of a vector space. Actually, the dimension of a vector space V over F is the number of elements in the basis. Okay, we know that this particularly Rn is a vector space over R, and its basis contains n elements, so its a dimension of the corresponding space is going to be n. And also if we consider if vector space F over a field F, it means F is a field, then we know that F over F is a vector space. In this case, its a basis contains only one single non-zero vector, any non-zero vector in that field, and therefore its dimension will be exactly equal to 1. So this is another example of a vector space having dimension 1. Now we consider some important result regarding the dimension. The first one says that any two finite dimensional vector spaces over a field F of the same dimension are isomorphic. Because we know that if V is a vector space of dimension n, then it is always isomorphic to Fn. And suppose another is a vector space U, which is also having dimension n, then the same space is again isomorphic to Fn, and therefore un must be isomorphic to each other. Then we have this another result. If V is a finite dimensional over F and u1, u2 and so on um belongs to V are linearly independent. So if we have a set of m vectors which are linearly independent, then we can find the vectors um plus 1, um plus 2 and so on um plus r in V, such that this set becomes a basis of V. Because if we start with some linearly independent set of vectors, and if we add some vectors in that such that the whole set becomes linearly independent, ultimately we'll get some set which becomes a linearly independent and span the whole space, and finally we say that that set becomes a basis of a vector space. And this is the last result, which is again important result. If V is a finite dimensional vector space and if W is a subspace of V, then W is a finite dimensional, and that they satisfy this relation, that is dimension of W is less than or equal to dimension of V, and also the dimension of this quotient space V by W is equal to dimension of V minus dimension of W. So far in this lecture, we have studied the definition of linearly dependent and independent vectors. Then we have considered the basis of a vector space with some important results. And lastly, we have seen the dimension of vector space. In the next lecture, we are going to see the definition of home VW, that is set of all homomorphism from V to W. In fact, we are going to show that this home VW is actually a vector space, and we try to explore some important properties of a vector space. Thank you.